Okay. I think we're ready to dive into it here then. Okay. Any questions so far? All right. So here you see again another figure that shows you the juxtamedullary nephrons, those that send a loop of Henle all the way down deep into the cortex. Here you see the collecting ducts opening up here, the tip of the renal papilla. There's the openings, right, of the renal papilla, draining into the minor calyx, from the minor calyx into the major calyx, from the major calyx into the renal pelvis, all right, and from the renal pelvis here into the ureter, all right, into the ureter. Who said collecting duct? We've left the collecting duct a long time ago, didn't we? Right? That was before we even got to the minor calyx. You're good? All right. Okay. So, last thing. I gave you 3 primary functions for the kidney last time. They were regulate body fluid volume, meaning control the amount of water in the system, right? Number 2. Thank you. Regulate ion concentration of the body fluids. And number 3, removal of cellular waste. Major functions. That's a minor function, all right? Removal of cellular wastes, meaning nitrogen wastes, right? Okay. Those are the 3 functions. The way we're going to accomplish those 3 functions involves 4 events. Those are filtration, which I just showed you. All right, what is filtration? That's the generation of filtrate across the spiral of capillaries. That's a result of hydrostatic pressure. All right, and the capture of that filtrate into the Bowman's capsule, which is the entry point into the kidney tubule. All right, that's filtration. Good? If I filter plasma that contains cellular wastes across the capillaries and into Bowman's capsule, and I leave it in the tubule, and what moves the filtrate through the tubule? What keeps the filtrate moving through the tubule and ultimately contributes to a continuous production of urine? Blood pressure. Blood pressure does, doesn't it? Blood pressure here is driving the whole system, isn't it? Right? Does that make sense? Does that make sense? Blood pressure at the glomerulus. Right? Blood pressure here, as it produces filtrate, that filtrate as it's being produced is pushing all the filtrate that sits ahead of it. Right? So blood pressure is generating this process of filtration. Do you get that? All right. When you die, if you die of disease, not getting hit by a bus, all right? When you die, this is where you die, all right? Because if you have an infection, you have pneumonia, or if you have cancer, or whatever it is, eventually it leads to a drop in your blood pressure, right? And if your blood pressure goes down, what happens here? You stop generating filtrate. And if you stop generating filtrate, then you're no longer pushing those cellular wastes into the tubule. If you do push those cellular wastes in the tubule, they're going to stay in the tubule, in the tubule, in the tubule, and out they go as urine, right? In fact, since we're there right now, can we check off that 3rd function? Removal of cellular wastes? Because we accomplished it right here, didn't we? Right at the glomerulus, right? We generated a filtrate. It includes cellular wastes. And if we leave those in the tubule, proximal, loop of Henle, distal, collecting duct, out the renal papilla, into the minor calyx, have we just gotten rid of cellular wastes? Good? Done. Check that off then. All right? And as I said, if you have disease that causes inflammation, then your blood pressure goes down, right? And if your blood pressure goes down, you stop filtering, and why do you die? You die because your system becomes toxic. That's what happens, all right, when you die of cancer, when you die of pneumonia. It's that failure right there that really, when you say, what is it that really killed the cells, all right, it's that failure right there, drop of blood pressure. All right, so maintaining adequate blood pressure is super important, isn't it, to maintain what we call here the glomerular filtration rate. Does that make sense? Good name. Glomerular filtration rate. Generating enough filtrate to keep the system moving. Okay, good. All right, now, I said 4 events. The first one is filtration. All right? The second event is reabsorption. And reabsorption simply means removing something that's in the filtrate, in the tubule, and pulling it back into the blood, which means you're putting it back into the body. Right? You're keeping it. You're not going to be pissing it away. All right? You're keeping it. Does that make sense? You pull it out of here. That's called reabsorption. All right? The opposite of that, if I take something from the blood downstream of the glomerulus and put it into the kidney tubule, that's called secretion. All right? So, filtration happens at the glomerulus, right? Reabsorption happens from the tubule into the blood supply, and we'll see where that happens. I'll talk about it in just a sec. All right? Secretion is the opposite of that. It's from the blood, putting it into the kidney tubule, downstream of the original, downstream of the glomerulus. All right? So it didn't get in there at the glomerulus, but you're adding it in later, after the fact. You'll see why later. All right? And finally, once we drain that down the collecting duct and put it into the minor calyx, we are now carrying out the final event, which is excretion. Right? Excretion. So there's your 4 events. All right? Glomerular filtration, tubular reabsorption, tubular secretion, and urinary excretion. Okay? All right. Now, go ahead. No. It happens in both of them. All right? And there's other reabsorption elsewhere too. All right? So Christina, I haven't identified where these events occur. I just want you to recognize that these events are going to occur, and we'll get to that in just a sec. All right. Let's say another word about filtration here. All right? Because I've said that you have hydrostatic pressure. All right? Can I give you an image of what hydrostatic pressure is if you're having a hard time with that? Think of a water balloon with a little pinhole in it. All right? The pressure of water is pushing out against the skin of that balloon, and there happens to be a little place where it can escape. All right? So that's hydrostatic pressure, pushing that water out of that little breach. Okay? That's what's happening here. All right? At the glomerulus. Except in this case, you're generating blood pressure, and the little penetration in our balloon takes the shape of 2 elements. The capillaries of the glomerulus, which are fenestrated. You already know what that is. All right? They've got little holes in them. And then the beginning, or the inner surface of the Bowman's capsule is intimately wrapped around those capillaries. All right? So the inner surface, we could call it the parietal layer. No, we call it the visceral layer, right? The visceral layer of Bowman's capsule, the one that's around the capillary, all right? The visceral layer of Bowman's capsule is made up of a kind of cells called podocytes, all right? And podocytes are cells that have feet, hence the name podocyte, all right? Pod is your foot, okay? Podocytes, all right? And those have little extra fingers extending out called pedicels. And it is the space in between those little fingers that becomes the sieve. All right? So between the spaces between the pedicels of the podocytes and the fenestrations in the capillaries, you now have a filtering system where the openings are too small to let blood cells get out, and they're too small to let protein get through. All right? So when you excrete urine, there aren't antibody proteins in it. All right? There isn't albumin in it. All right? Blood plasma protein, unless you have some kind of renal disease. All right? And then you have a problem. All right? There are cases of infection where you end up clogging up those little spaces there and you get kidney failure. All right? Because you clog these up. All right? As antibodies and things start to bunch together and they all accumulate here and you stop filtering, all right, for that reason. Go ahead. So dialysis is replacing this entire system. Okay? All right? And maybe we'll say another word about that in a bit. All right, so good? We got it? So we know how the filtrate's generated. Blood pressure, all right, differential because of the different size of the efferent versus the afferent arterial causes hydrostatic pressure, all right. What's the pressure like? Blood pressure in capillaries is about 30 millimeters mercury, all right. And capillaries are leaky even at that blood pressure. The blood pressure here in this particular ball of capillaries is twice normal, 60 millimeters mercury, all right. So for delicate little capillaries, that's a very high pressure, and as a result, they are going to leak. And that's perfect. That's exactly what you want. It's leaking and it's being captured here within the Bowman's capsule, all right? And this is then the visceral layer, and this is the parietal layer of Bowman's capsule. And we can talk about this whole thing, all right, as a renal corpuscle, all right? That is the combination of the Bowman's capsule with its two layers and the glomerulus, all right? We can talk about that as a renal corpuscle, all right? And we can talk about, as we said, the visceral layer, the podocytes, the parietal layer is a simple squamous epithelium, all right? And the space in between here, we can call it the urinary space if we want, all right? Okay. All right. Now, when the filtrate is generated here, what does it contain? I said it doesn't contain blood cells, and it doesn't contain large proteins. What does it contain? It contains water. That was easy. Ions of all sorts, right? The ions that are in your blood plasma, the salts, the sodium, and the chloride ions we talked about, because it's extracellular water, isn't it? It's extracellular stuff. So it's got ions, sodium and chloride ions, and sugars. Oh, wait, sugars, that's good stuff, right? You want to piss that away? No. So you've got sugars in there, you've got amino acids in there, you've got vitamins there, you've got hormones in there, all the things that are in your blood plasma, some of which you want to get rid of. Do you want to get rid of hormones? Yes. You want to get rid of hormones so that your endocrine tissues are responding to what's now, not what was yesterday. All right? And so hormones, that's good. You want to get rid of those. All right? But do you want to get rid of goodies? I'm going to call them goodies, as in glucose and amino acids, certain vitamins. Huh? No. So, in the proximal tubule, what's going to happen? Reabsorption. All right? Now, if I just remove solutes like sugars and amino acids and stuff and leave all the water behind, all right, it's going to start to get pretty dilute in the kidney tubule, right? If I just remove all the solutes. In the proximal tubule, I'm going to reabsorb over 80% of the volume. And I'm going to do it in equal proportion, water and solutes. Okay? Water and solutes. And if I do it in equal proportion, then what is the osmolarity of the fluid here, or here, or here? Well, let's start out by saying, what's the osmolarity of your blood plasma? You remember from last time? 300. That's your magic number. So it's 300 here. 300 here. You just pressed across some blood plasma. The proteins don't account for much of your osmolarity, all right? So you pressed across blood plasma. It's 300. And I'm going to start to reabsorb, which means I'm pulling it out of the tubule and putting it into the peritubular capillaries, which means I'm putting it back into the blood, into the body, right? I'm saving it. Good. All right, reabsorption. By the time I get to here, to the end of the proximal tubule, I have reclaimed over 80% of the filtrate. All right? Now, let me help you for a sec, all right? Because that doesn't mean anything yet. 80% of what? All right. Every day, this system pushes 180 liters of plasma across into the tubule, all right? In total, all the tubules, all right? Every day you generate 180 liters of filtrate. How much urine do you produce a day? 1.5 liters, right? 1 to 2 liters, all right? So otherwise, are you pissing away 180 liters a day? No, right? So what do you know has to happen if I'm pushing 180 liters into this space every day? I better do a lot of reabsorption, and 80% of that is happening here, all right? I'm reclaiming the sugars, I'm reclaiming the amino acids, I'm reclaiming ions in equal proportion to water, so that what's left in the tubule is smaller in volume, but it's still 300. It's still isotonic with the blood plasma. Okay? All right? Now, you might ask, well, Dr. D, why did you make the 180 liters in the first place if you're going to reabsorb 80% of it right at the start? Why didn't you just, filter out 20 liters instead of 180 liters? Because what was the first thing we accomplished? We got rid of cellular wastes. So it was worth it to produce those 180 liters because we got all those cellular wastes into the tubule. Now we'll reclaim most of that liquid that has all the goodies in it. All right? But you had to produce that much filtrate, all right, in order to push all those wastes in there. Now let's reclaim stuff. Okay? Good? All right? So, gets us to here. All right? We've checked off one function. We've reduced the volume of filtrate significantly. All right? Now we get to the loop of Henle. The loop of Henle, sometimes people say the loop of Henle concentrates the urine. They'd be wrong. All right? The loop of Henle does this. Listen. Under conditions of dehydration, the loop of Henle creates the potential to produce a concentrated urine. Think about it. If you're dehydrated, what kind of urine do you want to produce? Small volume and concentrated, right? Okay. So, under conditions of dehydration, the loop of Henle creates the potential to excrete a concentrated small volume of urine. All right? And conversely, under conditions of overhydration, you've drank way too much water, too much liquid, sitting at the pub too long, all right? The loop of Henle creates the potential to excrete large volume of dilute urine. Now, the key word, as you heard me accentuate it, is the potential, all right? The potential. It's just setting us up to be able to manage these things, all right? So, how does it do that, all right? The loop of Henle, as you're going to see, should I draw a clean one? Should we get a clean slate going here? Yeah, why not? Let's do that real quick. All right. The potential to excrete small volume of dilute urine, right? If you're dehydrated, what do you want to do? Small volume, concentrated, right? And if you're overhydrated, what do you want to do? Large volume of dilute, right? Okay, there it is. Okay, you got it. All right, so let's get our tubule up here again. All right, Bowman's capsule, proximal, loop of Henle, distal, and collecting duct. All right, by the way, the collecting duct is actually serving about 200 tubules. All right? So the collecting duct is here, and there's about 200 of these tubules that are plugging into it. So it isn't a one-to-one that every tubule has its own collecting duct. It's shared. Okay. No big deal. All right? Glomerulus, afferent arteriole, glomerulus, efferent arteriole, all right, and we're generating our filtrate of the blood plasma, and we're pulling out the goodies, all right? We won't draw the blood capillaries here. You know they exist now, all right? We're reabsorbing 80% of the goodies, and that reabsorbing is happening isotonically, meaning we're not changing the concentration. We're removing water and solutes in equal proportion so that it's 300 here, it's 300 here, it's 300 here, okay? Now, the loop of Henle is going to do this for us. It's going to generate a gradient of salt concentrations, all right? And I'm going to lie to you here. I'll just be honest, all right? I'm going to simplify this, all right? Another day I'll tell you the real story, all right? But I'll give it to you I know you don't like that, but you'll get this in physiology. You get it maybe in a little more detail, all right? But we'll get it enough that you get it, all right? If you were to buy a kidney at the butcher market, all right, and cut it in a nice coronal section like this, and begin to probe it with your tongue. All right, besides the fact that it would taste like pee, all right, you would find that it's very salty here, and it's less salty here, and less so here. And when you got up here, it would taste exactly like your blood plasma. All right, in other words, the saltiness up here is about 300. All right, and as you go down, we'll say 500, all right, and 700. And by the time we get down here, it's 1,200, all right? 1,200 is what? That's 4 times the saltiness of your blood plasma, right? Your blood plasma is 300. This is 1,200, okay? All right. So this gradient exists here as a result of the actions of the loop of Henle, all right? Let's see how it does this, and then we'll see what it's good for. Okay? This is our loop of Henle. This is called the descending limb. The liquid is going down. This is called the ascending limb. All right? Are we good? Stay with me. All right? The descending limb of the loop of Henle is permeable to water. All right? And if it's permeable to water, and we said it's 300 in here, and it's 300 out here, and blood pressure is, healthy blood pressure, you're generating filtrate, it's moving the filtrate through the tubule, then all of a sudden, this 300 blood plasma is down here now, and outside it's 500. It's more concentrated, more salty out here than it is in here, isn't it? And if this descending limb is permeable to water and not permeable to salt, what's water going to do? Water moves out. Water moves out. Water moves out. Where's that water going? Back to the body. It's being picked up by that Vasa recta. All right. Otherwise, this will be a swimming pool out here. Okay. It's picked up by the Vasa recta. But you're pulling water out. What's happening to the concentration in the tubule? It's becoming saltier. It's trying to reach equilibrium with what's outside the tubule. Right? It's trying to reach equilibrium with what's outside the tubule. So it's getting saltier and saltier. And by the time we get down here, it's 120. All right? Now, when we go round the bend here, 1,200. When we round the bend here, the properties of this loop of Henle change. All right? It's no longer permeable to water, but it is permeable to salt, to sodium chloride. All right? It's permeable to sodium chloride. All right? Permeable to Na plus and Cl minus. All right? And watch what happens, guys. The blood pressure pushes this. This is 1,200. It pushes it around. So it's 1,200 here, and it's only 1,000 here. What's salt going to do? Go out. Salt goes out. It's 1,000 here. It's 800 here, and it's only 700 out here. What's salt going to do? Salt's going to go out. Salt's going to go out. Salt's going to go out. And the last part of the loop of Henle, this is called the fin arm, and it gets a little fat and chubby here. All right, in the last part, because there's actually active transport proteins that are going to kick out even more salt by active transport. So when we get up here, guess what the number is up here? 100. It's even more dilute than your blood plasma. All right? Now that 100, that's the weakest urine you can produce. All right? That's the weakest urine you can produce. Okay? So, what have we done, you guys? By pulling water out, we concentrated this. And by concentrating it, that allowed us to pull salt out, didn't it? The water that we pulled out is picked up by the blood plasma, isn't it? So what is the loop of Henle doing for us? It's generating the salt gradient. All right? I began by showing you the salt gradient without telling you where it came from. Then I showed you how the loop of Henle works. And now you see where the salt gradient, how it got there. All right? And as long as blood is flowing, you're maintaining that salt gradient. All right? Okay? So you now have this nice gradation here, all right, of salts. Let's put it to work, all right? Under conditions of overhydration, the loop of Henle creates the potential to large volume dilute urine, right? Guess what? If I take this 100 here and I allow it to traverse through the distal tubule and I don't change it in any way, and I allow it to drain into the collecting duct, and I don't change it in any way, what am I going to excrete? Dilute urine. There it is. Check. Right? Under conditions of overhydration, the loop of Henle, by changing the filtrate to 100, is allowing me to dilute, to excrete very dilute urine, 100 milliosmolar. All right, a third the salt concentration of your blood plasma. I'm getting rid of more water than salt. Okay? All right? Good? Everybody? All right, now, if you're dehydrated, by the way, our gradient, just to be sure, you guys know this already, but your gradient is here, isn't it? This is the salt gradient, isn't it? Right? Okay. All right. If you're dehydrated, cells in your hypothalamus, all right, right in the center of your brain, all right, cells in your hypothalamus sense that the blood plasma has gotten salty. It's more than 300, all right, and they signal certain cells. Well, if it's salty around those cells, what are those cells going to do? Swell or shrink? They're going to shrink. When those cells shrink, all right, their distal ends, which sit in the posterior pituitary, all right, release a hormone called antidiuretic hormone.
Is that what causes?
No, sorry.
Is that what causes the headache when you're dehydrated?
No. So you're dehydrated. Your plasma is a little saltier than it should be. You have less water than you should, right? That causes those cells in the hypothalamus to shrink. When they shrink, those cells have a process that runs down into your posterior pituitary, and they release a hormone called antidiuretic hormone. All right? Now think about the name. Diuresis means you're peeing a lot. All right? You're dehydrated. Do you want to pee a lot? Hence the name antidiuretic hormone. And guess what ADH does? ADH acts on the collecting duct, all right, to increase the permeability to water. All right, on the collecting duct. All right. Tell me what happens. The gradient's running all the way across here, you guys, and all of a sudden I've just opened up this membrane to water movement. What's water going to do? Water's going to go out, right? Water's going to go out. Now, when I say go out, what do we really mean? Back into the body, all right? And so watch what happens here. As that filtrate passes down, the filtrate is trying to go into equilibrium with the salt gradient, isn't it? And if I release a lot of ADH, it's going to get more and more and more and more and more concentrated until it reaches equilibrium with 1200. All right? That's the best urine you can make. All right? 1200. Okay?
So when people have issues going back and they need to pee
So if like when you drink coffee, all right, coffee's a diuretic, all right. What does coffee do? It binds up the ADH that's in your system, all right. Okay. Beer has a number of effects. It binds up the ADH. It prevents you from producing more ADH. All right. It binds up the ADH and it prevents you from producing more ADH, and so you excrete a lot more. Okay, you excrete a lot more. So with your loop of Henle, you have the ability to dilute the filtrate and excrete it in that form to get rid of excess water. In the case of overhydration, in the state of overhydration, you excrete a dilute urine, large volume. And because that loop of Henle generated this salt gradient, right, in the face of dehydration, with the help of ADH and the salt gradient that was generated by the loop of Henle, it created the potential to pull water out of the collecting duct and do what to the urine? And concentrate the urine. All right? There's a little animal that lives in the desert. It's called a kangaroo rat. Okay? The kangaroo rat has a really long loop of Henle. It goes all the way down to the floor. All right? Guess what? It can concentrate its urine 12 times. All right? Not 4 times. It can concentrate its urine 12 times. All right? There's a little animal in Australia called the Australian hopping mouse. All right? It's got a really long loop of Henle. It can concentrate its urine 22 times. All right? Takes a leak, it's a puff of smoke. All right? No, it's not. But it's very concentrated. All right? It's very, very concentrated. Okay? All right. You saw that. You saw that coming. I know you did. All right. So, there we go. Are we good? You got it? All right. So, for a sec, go back a second. What did we say? That 80% of the kidney tubules are cortical. Do we need a lot of these loops of Henle, or can I rely on this one to generate gradient for all the adjacent collecting ducts? There you go. So you don't need to have 2.5 million loops of Henle. All right? If you just have, a couple 100,000, you're good to go. Okay? Literally. Okay? And the rest are going to make use of those loops of Henle. Go ahead.
Right. It's sort of unclear that, so the loop of Henle is what creates the concentration gradient.
That's right.
But the way that you explained the concentration gradient happening is because of the concentration gradient that's already there.
It was already there.
So how did it get there?
It formed as the organ developed. All right? And it's always there. All right? It's always there. Now, the lie that I've told you, that I confessed to earlier already, is that the gradient really isn't 3 to 1200, except if you're already sort of dehydrated. It's really like 3 to 600. All right? But if you're dehydrated, the gradient intensifies. So the gradient isn't a constant thing. It's not always 300 to 1200. All right? It's usually like 3 to 6 or 3 to 700. All right? But if you get dehydrated, it starts to intensify. And there's more to it, but I'm not going to tell you more than that right now. Okay? All right, you got it? Everybody's good? This is huge. All right? This is a lot. You got it? All right. Let's see if we can just wrap up a couple of things here. So I have shown you the loop of Henle creates the potential, right? And I'm going to skip that slide for just a moment. So we've talked about this already. We talked about antidiuretic hormone acting on the collecting duct. Here's a hormone produced by your posterior pituitary gland. Where's your posterior pituitary? It's sitting in the sella turcica of your sphenoid bone. Remember that? All right? And it's responding to the cerebrospinal fluid. All right? Okay? And it releases that ADH. It circulates through your whole body and has its action on the collecting duct, all right, allowing you In the case of overhydration, the duct is impermeable. You end up producing dilute urine, right? Any ADH in your system when you're overhydrated? No. All right? Only when you're dehydrated, and then in the case of dehydration, you have this idea, all right? ADH acts on the collecting duct, increases permeability to water. Water moves out of the collecting duct, back into the blood, and therefore the urine you produce is concentrated. All right, let's go back to this slide now. All right? Because, by the way, go ahead, check off number 1 of our 3 functions, right? Regulate body fluid volume. Didn't we just do that? That's what we just did, right? So we've got one more. Let's do it. We can do it real quick. Regulating ion concentration of the body fluids, okay? All right, regulating ion concentration. How are we going to do that? You've got cells in your adrenal gland. Where's the adrenal gland? It's sitting right here. Sits right on top of your kidney, like a little French chapeau up there, a little hat, all right? Okay, right on top of your kidney. And it's got cells in the adrenal cortex, the outer layer, that are sensitive to the amount of sodium in your blood plasma, all right? If sodium levels go down, all right, if sodium levels go down in the blood plasma, they're sensed by this gland, and it produces a hormone called aldosterone. All right? And aldosterone acts right here on the distal convoluted tubule. All right? So, if sodium levels go down, aldosterone is released. That acts on the distal convoluted tubule. To cause the reabsorption of sodium. Distal convoluted tubule. Reabsorption of sodium. All right? Sound good? Sodium levels were going down. When I say reabsorption, what do I mean? I'm pulling it out of the filtrate, putting it back in the body. So I'm elevating that. Now, the other thing it does is it causes the secretion of potassium. All right? It's a good place for us to almost stop, because we're going to finish this thought, but you're going to put it all together here. All right? It causes the reabsorption of sodium. So I'm reclaiming sodium out of the urine with extra effort, thanks to aldosterone. But I'm also secreting potassium. Why? Because the balance, right? We've said potassium is the intracellular ion, and sodium is the extracellular ion. So look, guys, here it is. Normally, you have this balance, right, between sodium concentration outside, potassium concentration inside. You're maintaining isotonic, all right? And what did we just say? Sodium level went down, right? What's going to happen to your cells in your body? Sodium level's down. Cells are going to swell, right? Water's going to move into the cells. So aldosterone gets released. And what is it doing at the kidney? It's causing you to reabsorb sodium, isn't it? To reclaim it out of the filtrate, right? But you're worried about the movement of water. So wouldn't you be smart to not only reabsorb sodium, but get rid of some potassium? Because the key is not, I need all the sodium back. The key is what? The balance. All right? That's why you have those two events happening. Reabsorption of sodium, pulling it out of the filtrate back into the blood, and secretion. Secretion is what? It's from the blood, pulling it from the blood and putting it into the blood or into the filtrate, right? And getting rid of excess, all right, potassium. All right? Check off the third function, all right? And the other stuff, pH regulation, guess what? The two tubules, especially the distal one, can secrete hydrogen ions, which is going to lower or going to raise your pH, right? Or they can secrete bicarbonate, okay, to have the opposite function on your body's pH. All right? Good? All right. So we are essentially done with what's happening in the kidney. When we come back on Tuesday, we'll talk about the rest of the urinary system. That is the ureter, the bladder, the urethra. Easy, easy, easy stuff. Read about it in your book. All right? We'll just blast through it. All right? And get on to reproduction.